Imagine walking into a textile factory in Lyon, France, in the year 1804. The air is thick with cotton fibers, and the rhythmic clacking of looms fills your ears. But one loom stands apart from the rest. This machine doesn't need a human operator guiding every thread. Instead, it reads a series of punched cards, automatically weaving intricate patterns with a precision that amazes even the most skilled craftsmen. This is the Jacquard loom, and you're witnessing the birth of programmable machines. Joseph Marie Jacquard had no idea that his invention would become the foundation for what we now call computer programming. The concept was revolutionary yet simple. Each card in the sequence had holes punched in specific positions. When a hole was present, a hook would pass through, lifting certain threads. When there was no hole, the hook was blocked, leaving those threads in place. Different patterns of holes created different weaving patterns. Change the cards, change the pattern. It was the first time in human history that a machine could be programmed to perform complex, variable tasks. But Jacquard faced fierce resistance. The skilled weavers of Lyon saw his machine as a threat to their livelihoods. They rioted, destroying several of his looms and even burning him in effigy. Sound familiar? This pattern of innovation meeting resistance would repeat throughout the history of computing. Yet Jacquard persevered, and by 1812, there were over 10,000 Jacquard looms operating across France. What made Jacquard's invention so significant wasn't just its immediate impact on textile production. It was the underlying principle, the separation of the machine's hardware from its instructions. The loom itself remained the same, but by changing the sequence of punch cards, you could create entirely different products. This concept of stored instructions would become fundamental to all computers. Now, let's travel 30 years forward to 1834, to the cluttered workshop of Charles Babbage in London. Babbage, a Cambridge mathematics professor, was frustrated by the constant errors in mathematical tables used by astronomers, navigators, and engineers. These tables, calculated by hand, were riddled with mistakes that could lead to ships running aground or engineering disasters. Babbage had a vision. What if a machine could calculate these tables automatically, eliminating human error entirely? His first attempt was the difference engine, a mechanical calculator designed to compute polynomial functions using the method of finite differences. The British government, recognizing the potential for more accurate navigation tables, funded the project with the enormous sum of £17,000. But Babbage was a perfectionist, working with the limited manufacturing techniques of the 1830s. The precise gears and wheels required tolerances that were nearly impossible to achieve with the technology of the time. As work on the difference engine stalled, Babbage's mind raced toward an even more ambitious concept. In 1837, he began designing what he called the analytical engine. This wasn't just a calculator. It was a general-purpose computing machine that could be programmed to perform any mathematical operation. The design was breathtaking in its complexity and foresight. The analytical engine had four main components that would be recognizable to any modern computer scientist. The mill was the processing unit, where calculations occurred. The store held numbers and intermediate results, functioning as memory. The operator controlled the sequence of operations, acting as the control unit. And most remarkably, it used punched cards for input and instructions, directly inspired by Jacquard's loom. Working alongside Babbage was Ada Lovelace, daughter of the poet Lord Byron and a mathematical genius in her own right. Ada understood the analytical engine's potential in ways that even Babbage sometimes missed. In 1843, she published what many consider the first computer program, a detailed algorithm for calculating Bernoulli numbers on Babbage's machine. But more importantly, she envisioned uses beyond pure calculation. In her notes, Ada wrote prophetically, "The analytical engine might act upon other things besides number, were objects whose mutual fundamental relations could be expressed by those of the abstract science of operations." She imagined a machine composing music, creating art, and processing any information that could be reduced to symbols and rules. Ada Lovelace had glimpsed the future of computing a century before it arrived. Unfortunately, the analytical engine was never completed. The precision manufacturing required was beyond the capabilities of Victorian engineering, and the British government, already frustrated by the difference engines, cost overruns, refused further funding. Babbage spent the rest of his life refining the design, but it remained on paper. It would be over a century before his vision was fully realized. The ideas of Babbage and Lovelace might have remained historical curiosities if not for the work of Herman Hollerith in America during the 1880s. Hollerith, a young engineer working for the U.S. Census Bureau, faced a daunting challenge. The 1880 census had taken 8 years to complete by hand, and with America's rapidly growing population, the 1890 census threatened to take even longer. At this rate, one census wouldn't be finished before the next began. Hollerith remembered the Jacquard loom principle and applied it to data processing. He developed a system where information about each person was encoded onto a punched card. Age, occupation, birthplace, and other census data were represented by holes punched in specific positions. These cards could then be processed by electrical machines that read the patterns of holes. His tabulating machine was elegantly simple. A card was placed over a bed of mercury-filled cups. Pins pressed down on the card, and wherever there was a hole, a pin would make contact with the mercury, completing an electrical circuit. This closed circuit would advance a mechanical counter, tallying the data automatically. Different combinations of holes could be counted simultaneously, allowing complex cross-tabulations that would have taken human clerks months to complete. The 1890 census was a triumph for Hollerith's system. What had taken 8 years was completed in just 2.5 years, despite a 25% increase in population. The cost savings were enormous, and the accuracy was far superior to manual methods. More importantly, the detailed statistical analysis possible with machine processing provided insights into American society that had never been available before. Hollerith founded the Tabulating Machine Company in 1896, which would eventually become part of International Business Machines, or IBM. His punched card system became the standard for data processing for the next 70 years. Banks used it for accounting, insurance companies for policy management, and governments worldwide for census taking. The familiar rectangular punched card, with its neat rows and columns of potential holes, became the primary way humans communicated with machines well into the computer age. But mechanical and electromechanical devices had their limitations. They were slow, prone to mechanical failure, and couldn't handle the complex calculations increasingly needed by science and engineering. The early 20th century brought new challenges that would push inventors toward fully electronic solutions. The rise of electrical engineering in the early 1900s created demand for complex mathematical calculations. Power grid analysis, radio circuit design, and the emerging field of aeronautics all required solving systems of equations that were impractical to handle by hand. Mechanical calculators, even sophisticated ones, were too slow and limited. Enter Vannevar Bush at MIT in 1927. Bush built what he called a differential analyzer, a massive mechanical computer that could solve differential equations. This room-sized machine used shafts, gears, and wheel and disc integrators to perform continuous calculations. Unlike earlier digital machines that worked with discrete numbers, Bush's analyzer could handle the smooth, continuous mathematics of engineering problems. The differential analyzer was incredibly impressive for its time, solving an hour's problems that would take human mathematicians weeks. But it had a crucial limitation. It was analog, not digital. Each problem required physically reconfiguring the machine, connecting different mechanical components in new ways. Programming meant literally rebuilding parts of the computer with wrenches and screwdrivers. As the 1930s progressed, the limitations of purely mechanical calculation became increasingly apparent. In Germany, Konrad Zuse was experiencing these frustrations firsthand. Trained as a civil engineer, Zuse was tired of the tedious calculations required for structural analysis. In his spare time, he began designing a machine that would automate these calculations using binary arithmetic and electromechanical relays. Zuse's Z1, completed in 1938, was the world's first programmable binary computer. Built in his parents' living room from metal plates cut with a jigsaw, the Z1 used mechanical memory and a mechanical arithmetic unit. Programs were read from punched paper tape, directly inspired by Jacquard's looms. Though the mechanical components proved unreliable, the Z1 demonstrated the feasibility of automatic calculation using binary logic. His next machine, the Z3, completed in 1941, replaced the unreliable mechanical components with electromagnetic relays. The Z3 was fully functional and arguably the world's first working general-purpose computer. It could perform floating-point arithmetic, handle conditional operations, and execute programs stored on punched film. Unfortunately, Zeus was working in isolation during World War II, and his achievements remained largely unknown to the broader scientific community until after the war. Across the Atlantic, similar developments were taking place. At Harvard University, Howard Aiken was collaborating with IBM to build the automatic sequence controlled calculator, later known as the Harvard Mark I. Completed in 1944, this electromechanical computer used relays, counters, and mechanical calculators to perform complex calculations automatically. The Mark I was enormous, 51 feet long, 8 feet high, and weighing 5 tons. It contained over 3,000 electromechanical relays and could store 72 numbers. Programs were entered using punch paper tape, and the machine could run continuously for days, solving complex mathematical problems. Though slower than purely electronic computers that would soon follow, the Mark I proved that large-scale automatic calculation was practical and reliable. Grace Hopper, working with the Mark I team, became one of the first programmers in history, developing techniques for debugging programs and creating subroutines that could be reused in multiple calculations. Her work established many of the fundamental principles of programming that are still used today. When she found an actual moth trapped in the Mark I's relays, causing a malfunction, she taped it into the machine's logbook with the note, "First actual case of bug being found." The term computer bug was born. These electromechanical computers represented the final evolution of mechanical calculation. They combined the reliability and precision of mechanical devices with the speed and flexibility of electrical switching. More importantly, they demonstrated that machines could follow complex sequences of instructions automatically, performing calculations that would take human operators weeks or months to complete. The conceptual breakthroughs were now complete. Jacquard had shown that machines could be programmed using punched cards. Babbage and Lovelace had envisioned general-purpose computers that could manipulate symbols as well as numbers. Hollerith had demonstrated that data processing could be automated on a massive scale. Bush had proven that machines could solve complex mathematical problems. Zeus and Aiken had built working computers that combined all these concepts into practical, reliable systems. By 1945, the mechanical and electromechanical era of computing was drawing to a close. The fundamental concepts had been established: programmable machines, stored instructions, automatic calculation, and data processing. The engineering challenges of building reliable, large-scale computing systems had been solved. Most importantly, a small but growing community of engineers and mathematicians understood that these machines represented more than just faster calculators. They were the foundation for an entirely new relationship between humans and information. For the first time in history, machines could not only store and retrieve data, but also manipulate it according to complex logical rules. They could perform not just arithmetic, but genuine reasoning, following chains of inference too long and complex for human minds to track reliably. The stage was set for the next revolution: purely electronic computers that would operate at speeds thousands of times faster than their mechanical and electromechanical predecessors. The vacuum tube, initially developed for radio and telephone applications, would replace mechanical relays and enable computation at previously unimaginable speeds. The age of electronic computing was about to dawn, bringing with it capabilities that would transform not just calculation, but human civilization itself. The mechanical foundations laid between 1800 and 1945 had proven that machines could think, at least in the limited sense of following logical instructions to solve complex problems. They had established the fundamental architecture of computing: input devices, processing units, memory, and output systems. They had demonstrated that programming was possible and that data could be processed automatically on a massive scale. Now it was time to make machines think faster, more reliably, and more flexibly than ever before. The electronic revolution was about to begin, and with it, the transformation of computing from a specialized tool used by a few scientists and engineers into the foundation of modern technological civilization. The year is 1943, and the world is at war. In a basement laboratory at the University of Pennsylvania, two brilliant minds are about to change the course of human history. J. Presper Eckert and John Mauchly have been commissioned by the U.S. Army to build a machine that can calculate artillery firing tables faster than any human computer ever could. What they're creating will become known as the NIAC, the Electronic Numerical Integrator and Computer, and it will usher in the electronic age of computing. Picture this monster of a machine. ENIAC weighs 30 tons and fills an entire room. It contains over 17,000 vacuum tubes, 70,000 resistors, 10,000 capacitors, and 6,000 switches. When it's running at full capacity, it consumes as much electricity as a small town. The heat generated is so intense that one of the vacuum tubes burns out every other day on average. Yet despite these challenges, ENIAC represents a quantum leap forward from anything that came before. The key breakthrough is speed. While mechanical computers like the Harvard Mark I take several seconds to perform a multiplication, ENIAC can do the same calculation in less than 3 milliseconds. It can add numbers in just 200 microseconds. This might not sound impressive by today's standards, but in 1946, it's nothing short of miraculous. ENIAC can solve in 30 seconds a problem that would take human mathematicians 20 hours to complete. But the NIAC has a significant limitation that its creators don't fully appreciate at first. Programming it requires physically rewiring the machine. Teams of women, many of them mathematicians who had been working as human computers during the war, spend days or even weeks reconfiguring cables and setting switches for each new problem. These women, including Betty Snyder, Marlon Weskoff, and Ruth Lichterman, become the world's first computer programmers, though their contributions will be overlooked for decades. The programming process is incredibly laborious. To calculate a trajectory, the operators must trace the path of the computation through the machine, connecting different units with thick cables. A single mistake in the wiring can produce completely wrong results, and debugging requires checking thousands of connections by hand. Despite these challenges, the women who program ENIAC develop innovative techniques and become masters of this early form of computing. News of ENIAC spreads quickly through the scientific community. When it's publicly demonstrated in February 1946, newspapers around the world herald the dawn of the computer age. The New York Times calls it a giant brain, while other publications speculate about machines that might someday think like humans. The public is simultaneously fascinated and slightly terrified by this electronic marvel. But even as ENIAC is capturing headlines, its creators and others are already envisioning the next generation of computers. The challenge of rewiring the machine for each new program is clearly unsustainable. What if, instead of changing the hardware, you could store both data and instructions in the same memory? This concept, which seems obvious today, represents a revolutionary breakthrough in the 1940s. John von Neumann, the brilliant mathematician who had consulted on the ENIAC project, articulates this vision in a paper describing a proposed machine called EDVAC. Von Neumann's stored program concept means that a computer's memory would hold both the numbers it's working with and the instructions, telling it what to do with those numbers. Change the instructions in memory, and you've programmed the computer without touching a single wire. This insight transforms computer design. Instead of being fixed-purpose machines that must be physically reconfigured for different tasks, computers become truly general-purpose devices. A single machine can calculate payrolls in the morning, analyze scientific data in the afternoon, and play games in the evening, all by simply loading different programs into memory. The first stored program computer to actually run is built not in America, but in Manchester, England. In June 1948, the Manchester Baby, officially called the Small-Scale Experimental Machine, successfully executes its first program. The program itself is trivial, finding the highest factor of a number, but the principle is revolutionary. For the first time in history, a machine is modifying its own instructions as it runs. Meanwhile, Back in the United States, Eckert and Mauchly have left the University of Pennsylvania to start their own company. They're working on UNIVAC, the Universal Automatic Computer, which they promise will be faster, more reliable, and easier to program than ENIAC. But building computers is expensive, and their small company struggles financially. Eventually, they sell out to Remington Rand, but not before establishing many of the principles that will guide computer development for decades. UNIVAC makes its public debut in a most dramatic fashion. On election night 1952, CBS News decides to use UNIVAC to predict the outcome of the presidential race between Dwight Eisenhower and Adlai Stevenson. Early in the evening, with only a small percentage of votes counted, UNIVAC predicts an overwhelming victory for Eisenhower. The prediction seems so unlikely that the CBS team assumes the computer has made an error. They adjust the program to produce a closer result, more in line with human expectations. But as the night progresses and more returns come in, it becomes clear that UNIVAC's original prediction was correct. Eisenhower wins by exactly the landslide margin the computer had forecasted. The dramatic reversal, broadcast live on television, demonstrates the power of electronic computation to millions of Americans. Suddenly, computers aren't just tools for scientists and mathematicians. They're machines that can analyze complex patterns and make predictions that humans might miss. The success of these early electronic computers creates enormous demand, but there's a fundamental problem limiting their growth: vacuum tubes. These glass bulbs, essential for electronic switching and amplification, are bulky, hot, power-hungry, and unreliable. A computer with thousands of vacuum tubes requires constant maintenance as tubes burn out regularly. The heat they generate demands expensive cooling systems, and their power consumption makes operating costs astronomical. The solution comes from an unexpected source: Bell Telephone Laboratories. In December 1947, 3 researchers at Bell Labs, John Bardeen, Walter Brattain, and William Shockley, demonstrate a device they call a transistor. This small semiconductor device can perform the same switching and amplification functions as a vacuum tube, but it's smaller, more reliable, generates less heat, and uses much less power. The implications are staggering, though not immediately apparent. The first transistors are expensive and somewhat unreliable themselves. Many engineers are skeptical that these tiny devices can replace the familiar vacuum tube. But a few visionaries understand what transistors might make possible. Instead of room-sized computers costing hundreds of thousands of dollars, transistors could enable smaller, cheaper, more reliable machines. The transition happens gradually through the 1950s. Early transistorized computers, like the IBM 701, introduced in 1959, demonstrate the advantages of solid-state electronics. They're more compact, more reliable, and easier to cool than their vacuum tube predecessors. More importantly, they point toward a future where computers might become small enough and cheap enough for widespread use. But hardware improvements alone aren't enough to make computers practical for a broader range of users. The programming process remains incredibly difficult and error-prone. Early computers are programmed in machine language, requiring programmers to specify every operation in terms of binary numbers that the hardware can directly understand. Writing even simple programs requires intimate knowledge of the computer's internal architecture. A typical machine language program might look like a series of numbers: 011011101, 00110010. Each sequence tells the computer to perform a specific operation, like loading a number from memory, adding 2 numbers, or jumping to a different part of the program. Debugging these programs is nightmarish, as a single incorrect digit can cause the entire program to fail in mysterious ways. The breakthrough comes from recognizing that computers themselves can help with the programming process. If a computer can manipulate numbers, why can't it manipulate symbols that represent programming instructions? This insight leads to the development of assembly language, where programmers can write instructions using memorable abbreviations instead of pure numbers. Instead of remembering that 011011101 means load the contents of memory location into the accumulator, a programmer can simply write load A. The computer then translates these symbolic instructions into the machine language it actually understands. This translation process, performed by a program called an assembler, makes programming significantly easier and less error-prone. But even assembly language requires detailed knowledge of computer hardware. Different computers use different instruction sets, so a program written for one machine won't run on another. What programmers really need are languages that let them express solutions in terms closer to the problems they're trying to solve, rather than the peculiarities of particular machines. The first breakthrough in high-level programming languages comes from an unexpected source, a woman working at Remington Rand named Grace Hopper. Hopper, a former Navy officer with a PhD in mathematics, is working on programming the UNIVAC when she has a revolutionary idea. Instead of writing programs that manipulate numbers, why not create programs that can manipulate words and mathematical expressions that humans find natural? In 1952, Hopper develops the first compiler, a program that can translate mathematical expressions and English-like commands into machine language. Her system, called A0, lets programmers write instructions like compute the square root of b squared minus 4 times a times c. The compiler then figures out how to break this complex expression down into the simple operations that the computer can actually perform. Hopper faces enormous skepticism from her colleagues. Many programmers believe that anything other than hand-coded machine language will be too slow and inefficient for practical use. The idea that a computer program can write other computer programs seems almost like magic to many engineers. But Hopper persists, continually refining her compiler and demonstrating its practical advantages. The real breakthrough comes with the development of Fortran, formula translation, at IBM in the mid-1950s. Led by John Backus, the Fortran team creates a programming language specifically designed for scientific and engineering calculations. Fortran lets programmers write mathematical formulas in a notation that looks almost like traditional algebra, then automatically translates these formulas into efficient machine code. A Fortran program to calculate the roots of a quadratic equation might look like root 1 equals b plus sqrt, b asterisk asterisk 2 for ac, / 2 asterisk a. This is far more readable and understandable than the hundreds of machine language instructions required to perform the same calculation. More importantly, a Fortran program can run on any computer with the Fortran compiler, freeing programmers from the need to rewrite their programs for different machines. The impact of Fortran is immediate and profound. Programming time drops from weeks to days for complex scientific applications. Programs become more reliable because there are fewer opportunities for the kinds of detailed errors that plague machine language programming. Most importantly, scientists and engineers who aren't computer specialists can now write their own programs, dramatically expanding the community of computer users. But Fortran is designed primarily for mathematical calculations. Business applications require different capabilities, particularly the ability to process large amounts of textual and numerical data efficiently. This need leads to the development of COBOL, Common Business-Oriented Language, in the late 1950s. COBOL uses English-like syntax that makes business programs more readable to managers and accountants who might need to understand what the programs are doing. A COBOL program might include statements like add salary to total payroll, or if account balance is greater than credit limit, then print warning notice. While these statements are more verbose than Fortran's mathematical notation, they're much clearer to business users who need to verify that programs correctly implement company policies. The development of these early programming languages marks a fundamental shift in how humans interact with computers. Instead of being tools that only specialists can use, computers begin to become accessible to anyone willing to learn logical thinking and problem-solving skills. The gap between human thought processes and machine operations is narrowing, setting the stage for the explosive growth of computing in the decades to come. By the end of the 1950s, all the fundamental elements of modern computing are in place. Electronic hardware based on transistors, stored program architecture, and high-level programming languages. Computers are no longer room-filling monsters that only universities and large corporations can afford. They're becoming practical tools for an ever-widening range of applications, from business data processing to scientific research to engineering design. The The transformation from mechanical calculators to electronic computers represents one of the most rapid technological revolutions in human history. In just 15 years, computing has evolved from devices that filled entire rooms and consumed enormous amounts of power to machines that can sit on a desk and perform calculations that would have amazed the builders of ENIAC. More importantly, programming has evolved from the physical rewiring of hardware to the writing of instructions in languages that resemble human thought processes. Scientists and engineers, who once needed teams of human computers to perform complex calculations, can now write programs that solve the same problems in minutes rather than months. The economic impact is already becoming apparent. Companies like IBM are generating enormous profits from computer sales and service contracts. New industries are emerging around software development, computer maintenance, and data processing services. Universities are establishing computer science departments to train the programmers and engineers needed to support this growing field. But perhaps most significantly, the conceptual barriers between humans and machines are beginning to dissolve. Computers are no longer mysterious devices that only specialists can understand and operate. They're becoming tools that amplify human intelligence, extending our ability to solve problems, analyze data, and explore complex ideas. The stage is set for the next revolution, the development of integrated circuits that will make computers even smaller, faster, and more affordable, eventually putting computational power into the hands of millions of ordinary people around the world. The electronic revolution of the 1940s and 50s has established the foundation. Now it's time to build the future. The year is 1958, and Jack Kilby is having a problem. It's summer at Texas Instruments in Dallas, and while most of his colleagues are enjoying their vacations, Kilby, as the newest employee, is stuck at work. But this forced solitude is about to lead to one of the most important inventions in human history. As he sits in the quiet laboratory, staring at a collection of transistors, resistors, and capacitors scattered across his workbench, Kilby has a revolutionary thought. What if all these separate components could be built on a single piece of semiconductor material? The electronics industry is facing what engineers call the tyranny of numbers. As electronic devices become more complex, they require thousands of individual components, each of which must be manufactured separately and then connected by hand with tiny wires. A single computer might contain hundreds of thousands of solder connections, each one a potential point of failure. The process is expensive, time-consuming, and unreliable. Moreover, the physical size of all these components and connections is becoming a serious limitation. Kilby's insight is elegantly simple. Instead of building transistors, resistors, and capacitors as separate devices and then connecting them with wires, why not create them all from the same piece of silicon and connect them with paths etched directly into the material? On September 12, 1958, he demonstrates his first integrated circuit, a simple device containing just a few components built on a sliver of germanium less than half an inch long. The demonstration is crude by any measure. Kilby's integrated circuit is connected to external components with gold wires attached by hand, and it performs only the simplest of functions, an oscillator that produces a sine wave. But the principle is revolutionary. For the first time, multiple electronic functions are integrated into a single, monolithic structure. The age of the microchip has begun. Meanwhile, 6 months later and 3,000 miles away, Robert Noyce at Fairchild Semiconductor in California is working on the same problem with a different approach. Noyce, who would later co-found Intel, develops a more practical method for creating integrated circuits using silicon instead of germanium, and more importantly, he figures out how to make the connections between components using aluminum pathways deposited directly on the silicon surface. This eliminates the need for hand-attached wires and makes mass production possible. The race to commercialize integrated circuits begins immediately. Both Texas Instruments and Fairchild rush to develop practical applications, initially focusing on military and aerospace markets, where the premium price of these new devices can be justified by their superior reliability and compact size. The Apollo Moon program becomes an early adopter, using integrated circuits in the guidance computers that will navigate astronauts to the lunar surface. but it's the commercial potential that truly drives the rapid development of integrated circuit technology. As manufacturing processes improve, the cost per circuit drops dramatically while performance increases. The first integrated circuits contained just a few transistors, but engineers quickly learned to pack more and more components into the same amount of space. This rapid improvement catches the attention of Gordon Moore, director of research at Fairchild Semiconductor. In 1965, Moore makes an observation that will become one of the most famous predictions in technology history. He notices that the number of transistors that can be placed on a computer chip has been doubling approximately every year, and he predicts this trend will continue for at least 10 years. Moore's observation, which becomes known as Moore's Law, is more than just a technical prediction. It becomes a roadmap for the entire semiconductor industry. Companies begin planning their research and development efforts around the assumption that chip performance will double regularly, while costs remain roughly constant. This creates a virtuous cycle. As chips become more powerful and less expensive, new applications become economically feasible, which drives demand for even better chips. The implications of Moore's Law extend far beyond the semiconductor industry itself. Computer designers begin planning systems around the assumption that tomorrow's chips will be significantly more powerful than today's. Software developers start writing programs that would be impossibly slow on current hardware, knowing that by the time the software is finished, the necessary computing power will be available at an affordable price. But the benefits of integrated circuits aren't immediately obvious to everyone in the computer industry. The established computer manufacturers, led by IBM, have invested enormous resources in transistor-based systems. IBM's System/360 series, introduced in 1964, represents the pinnacle of transistor computer technology. These machines are incredibly powerful and reliable, serving as the backbone of corporate America's data processing needs. The System/360 is a family of compatible computers, a revolutionary concept at the time. Previously, upgrading to a more powerful computer meant completely rewriting all your software. IBM's innovation is creating a range of machines, from small business systems to powerful scientific computers, that all use the same instruction set and can run the same programs. A company can start with a modest System/360 Model 30 and upgrade to a more powerful Model 75 without losing their software investment. This compatibility comes at a cost, however. IBM's engineers must design all the machines in the series to support the same features, even when some of those features aren't needed for particular applications. This leads to computers that are more complex and expensive than they need to be for many tasks. The stage is set for a different approach to computer design. The challenge comes from an unexpected direction. Ken Olsen and his team at Digital Equipment Corporation in Massachusetts, DEC, founded in 1957, takes a radically different approach to computer design. Instead of trying to build machines that can handle every possible application, they focus on creating smaller, simpler computers optimized for specific tasks. Their first major success is the PDP-1, introduced in 1960. At $120,000, it costs less than one-tenth the price of a comparable IBM mainframe, yet it provides impressive performance for scientific and engineering applications. The PDP-1 is designed to be operated directly by the person using it, rather than by a specialized computer operator. This interactive computing model is revolutionary in an era when most computers are batch processing systems that run one job at a time. The PDP-1 introduces many people to the joy of interactive computing. At MIT, students use the PDP-1 to create Space War, one of the first computer games. The game, which simulates a battle between two spaceships orbiting a star, spreads to PDP-1 installations around the country and becomes a cultural phenomenon in the small but growing community of computer enthusiasts. DEC follows the PDP-1 with an even more successful machine, the PDP-8, introduced in 1965. At $18,000, the PDP-8 is the first computer to cost less than $20,000, a psychological barrier that opens up entirely new markets. Small businesses, academic departments, and research laboratories that could never afford a mainframe suddenly find computing within their reach. The PDP 8 is built around integrated circuits, making it much smaller and more reliable than transistor-based competitors. The entire computer fits in a single rack about the size of a refrigerator, compared to the room-filling installations required by mainframes. This compact size enables new applications. Computers can now be embedded in laboratory instruments, manufacturing equipment, and other specialized devices. The success of mini-computers like the PDP-8 fundamentally changes the computer industry. For the first time, computing power is decentralized. Instead of a single, powerful mainframe serving an entire organization, departments and workgroups can have their own dedicated computers. This leads to more interactive and responsive computing experiences, as users no longer need to compete with hundreds of others for access to a shared system. But mini-computers also create a new problem: isolation. Each computer is essentially an island, with its own programs and data that can't easily be shared with other systems. As organizations acquire multiple computers, the need to connect them becomes increasingly apparent. The solution will require developing entirely new technologies for computer networking. The foundation for computer networking is laid in the late 1960s by the Advanced Research Projects Agency, ARPA, a division of the U.S. Department of Defense. ARPA is funding computer research at universities and research institutions across the country. But researchers at different sites have no easy way to share their work or collaborate on projects. J.C.R. Licklider, the director of ARPA's Information Processing Techniques Office, envisions a network that would connect research computers, allowing scientists to share resources and collaborate regardless of their physical location. The technical challenges are enormous. Different computers use incompatible communication protocols and data formats. Phone lines, the only practical long-distance communication medium available, are designed for voice communication and are poorly suited to digital data transmission. Most fundamentally, nobody has ever built a network designed to connect different types of computers located hundreds of miles apart. The solution comes from a team led by Larry Roberts at ARPA and Leonard Kleinrock at UCLA. Their approach is revolutionary. Instead of trying to create direct connections between every pair of computers, they design a network of specialized computers called interface message processors, or IMPs, that handle the job of routing messages between systems. Each research site gets an IMP that connects to their local computers and to other IMPs over long-distance phone lines. The first ARPANET connection is established on October 29, 1969, between UCLA and Stanford Research Institute, about 300 miles apart. The first message transmitted is appropriately simple: "Hello." The UCLA team had intended to type login, but the system crashed after just 2 letters. Despite this inauspicious beginning, the connection works, and computer networking is born. Within a year, 4 sites are connected to ARPANET: UCLA, Stanford, UC Santa Barbara, and the University of Utah. The network grows rapidly as more research institutions join. But the real breakthrough comes when researchers begin using the network for purposes beyond its original design. Electronic mail, invented almost by accident by Ray Tomlinson in 1971, becomes the network's most popular application. The ability to send messages instantly between researchers at different institutions transforms the pace of collaborative research. The development of ARPANET coincides with rapid improvements in integrated circuit technology. By the early 1970s, it's possible to build complete computer processors on single chips. Intel, founded in 1968 by Robert Noyce and Gordon Moore, introduces the 4004 microprocessor in 1971. This single chip contains the processing power of early room-sized computers, though it's designed primarily for use in calculators and other simple devices. The 4004 is followed by increasingly powerful microprocessors, the 8008 in 1972, and the breakthrough 8080 in 1974. The 8080 is the first microprocessor powerful enough to serve as the foundation for a general-purpose computer. At the same time, memory chips are becoming denser and cheaper, making it economically feasible to build complete computers around microprocessors. This convergence of powerful microprocessors and cheap memory sets the stage for the next revolution in computing. If a complete computer can fit on a few integrated circuits, why should computers remain expensive, room-filling devices accessible only to large organizations? The stage is set for computing to become truly personal. But the transition won't be smooth. The established computer industry, built around mainframes and mini-computers, is slow to recognize the potential of microprocessor-based systems. Most industry executives view microcomputers as toys, suitable only for hobbyists and simple applications. They can't imagine that these simple devices will eventually challenge and ultimately surpass the powerful systems that generate their profits. The resistance isn't entirely unreasonable. Early microcomputers are indeed limited in their capabilities. They have tiny amounts of memory, no permanent storage, and rudimentary software. Programming them requires detailed knowledge of assembly language and hardware interfaces. The idea that ordinary people, not just computer specialists, might want to own and use computers seems absurd to most industry observers. Yet the foundation is being laid for a transformation that will dwarf all previous changes in computing history. The combination of integrated circuits, microprocessors, and networking technologies, developed in the 60s and 70s, will soon enable computing to escape from corporate data centers and research laboratories, putting computational power directly into the hands of millions of ordinary people. The economic implications are staggering. The computer industry, which has been a relatively small specialty market serving large organizations, is about to expand to serve every business and eventually every household in the developed world. The social implications are even more profound, as computing power becomes accessible to individuals, small groups, and organizations that were previously excluded from the digital revolution. As the 1970s draw to a close, all the necessary technologies are in place. Integrated circuits have made computers small and affordable. Many computers have demonstrated that interactive computing is more productive than batch processing. Networking has shown that connected computers are more valuable than isolated ones. Microprocessors have proven that complete computers can fit on single chips. What's missing is the vision to bring these technologies together in ways that serve ordinary people rather than just computer specialists. That vision is about to emerge from an unlikely source. Hobbyists and entrepreneurs working in garages and spare bedrooms, people who see computers not as business tools or scientific instruments, but as amplifiers of human creativity and intelligence. The integrated circuit revolution has democratized access to computing power in ways that seemed impossible just a decade earlier. Where once only large corporations and universities could afford computers, now small businesses, research groups, and even individuals can access computational capabilities that rival the most powerful systems of the previous generation. The networking revolution has shown that computers become exponentially more valuable when they can communicate with each other. The early ARPANET experiments have proven that researchers separated by thousands of miles can collaborate as effectively as if they were working in the same laboratory. Electronic mail has emerged as the most popular application on early networks, demonstrating that people have an enormous appetite for digital communication. Most importantly, the microprocessor revolution has made it economically feasible to embed computing power in devices and applications that were previously unimaginable. The 8080 and similar processors are being used not just in computers, but in industrial controls, scientific instruments, and consumer devices. The boundary between computers and other machines is beginning to blur. Moore's law continues to drive improvements in integrated circuit technology, ensuring that each new generation of microprocessors will be more powerful and less expensive than the last. This creates a predictable roadmap for innovation, allowing entrepreneurs and engineers to plan products around capabilities that don't yet exist, but will be available by the time their designs are completed. The convergence of these trends is creating unprecedented opportunities for innovation. For the first time in history, individuals and small teams have access to the same fundamental technologies that were previously available only to large institutions. The tools needed to create revolutionary products exist, waiting for visionaries who can imagine new ways to apply them. The personal computer revolution is about to begin, driven not by large corporations or government agencies, but by passionate individuals who believe that computing power should belong to everyone. The foundation has been laid through decades of innovation in electronics, software, and networking. Now it's time for the next chapter in the story of computing, putting these powerful tools directly into the hands of ordinary people and watching what they create. It's January 1975, and Ed Roberts is desperate. His small company, MITS, which stands for Micro-Instrumentation and Telemetry Systems, is on the verge of bankruptcy. Based in Albuquerque, New Mexico, MITS has been making electronic calculators, but the market has been flooded by cheap imports from Asia, and his business is dying. Roberts needs a new product, and he needs it fast. His solution will accidentally launch the personal computer revolution. Roberts has been watching the development of microprocessors with keen interest. Intel's new 8080 chip is powerful enough to serve as the brain of a real computer, not just a calculator. The problem is that Intel is charging over $300 per chip, making any computer built around it prohibitively expensive. But Roberts has a plan. He approaches Intel with an offer to buy the 8080 chips in bulk for a new computer kit he wants to build. If Intel will sell him chips for $75 each, he'll design a computer that hobbyists can assemble themselves. Intel agrees, partly because they don't think Roberts can sell very many computers anyway. They're wrong. Roberts designs a computer he calls the Altair 8800, named after a destination in a Star Trek episode. The Altair is incredibly basic, just a blue metal box with switches and lights on the front panel, no keyboard, no screen, no permanent storage. Programming it requires flipping switches to enter binary code directly into memory. But it's a real computer that individuals can actually afford to buy. Roberts needs a way to market his creation, so he contacts Popular Electronics magazine. The magazine's editors are immediately intrigued. They've been looking for a computer project that their readers might actually be able to build, and the Altair fits perfectly. The January 1975 cover story promises readers they can build a complete computer for under $400. The response is overwhelming. MITS receives over 4,000 orders in the first 3 months, each accompanied by a check for the full purchase price. Roberts has to hire dozens of additional employees and work around the clock to fulfill orders. But the Altair's success isn't just about the computer itself. It's about what it represents. For the first time in history, ordinary individuals can own their own computers. The Altair creates an entire ecosystem almost overnight. User groups spring up in cities across America, where enthusiasts gather to share programming tips and hardware modifications. Newsletters and magazines devoted to personal computing begin publication. Most importantly, entrepreneurs start companies to provide software and peripherals for this new market. Among the earliest of these entrepreneurs are 2 young men from Seattle, Bill Gates, 19 years old, and Paul Allen, 22. Both are Harvard dropouts with an obsession for programming. When they see the Popular Electronics article about the Altair, they immediately recognize an opportunity. The Altair needs software, and they know how to write it. Gates and Allen contact Ed Roberts with a bold proposal. They'll create a version of the BASIC programming language for the Altair. BASIC, which stands for Beginner's All-Purpose Symbolic Instruction Code, was developed at Dartmouth College as a simple language for teaching programming. It's perfect for personal computers because it's easy to learn and doesn't require the detailed technical knowledge needed for assembly language programming. There's just one problem. Gates and Allen don't actually have an Altair computer. They can't afford one. Instead, they write their BASIC interpreter on a DEC-PDP, 10 mini-computer at Harvard, using a program that simulates how an 8080 processor works. They're essentially writing software for a computer they've never touched, hoping it will work when they finally test it on real hardware. The gamble pays off. When Allen demonstrates their BASIC interpreter on an actual Altair at MITS headquarters in Albuquerque, it works perfectly. Roberts is impressed and licenses their software, which becomes the first commercial software program for personal computers. Gates and Allen form a company they call Microsoft, and the software industry is born. But the Altair has serious limitations. It's difficult to use, requires constant tinkering, and appeals mainly to electronics hobbyists. What the personal computer revolution needs is a machine designed for ordinary people, not just technical experts. That machine comes from an unlikely source: two college dropouts working in a garage in Los Altos, California. Steve Jobs and Steve Wozniak are members of the Homebrew Computer Club, a group of Silicon Valley enthusiasts who meet regularly to share ideas about personal computing. Wozniak, known to everyone as Woz, is a brilliant engineer with an intuitive understanding of computer hardware. Jobs is more interested in the business potential of personal computers. He has a vision of computers as consumer products, as easy to use as toasters or televisions. Wozniak's breakthrough comes in 1976 when he designs a computer that's far more sophisticated than the Altair, but actually simpler to use. His machine, which they call the Apple I, includes a built-in keyboard interface and can display text on an ordinary television set. More importantly, it comes fully assembled. Unlike the Altair, which arrives as a pile of parts that users must solder together, the Apple I is ready to use right out of the box. Jobs recognizes that Wozniak has created something special, but he also understands that the real breakthrough will come from making computers even more accessible. While Wozniak works on improving the hardware, Jobs focuses on creating a complete product that anyone can use. Their next computer, the Apple II, will transform personal computing from a hobbyist curiosity into a mass-market phenomenon. The Apple II, introduced in April 1977, is a revolution in design and usability. It comes in a sleek plastic case that looks more like a home appliance than an electronic device. It has color graphics capabilities that far exceed anything previously available on a personal computer. Most importantly, it includes features that make it genuinely useful for ordinary people. A built-in programming language, the ability to store programs and data on ordinary cassette tapes, and later, floppy disk drives for more convenient storage. But what really makes the Apple II successful is software, particularly a program called VisiCalc. Developed by Dan Bricklin and Bob Frankston, VisiCalc is the first electronic spreadsheet program. It allows users to create financial models and perform complex calculations by simply typing numbers and formulas into a grid of rows and columns. Changes to one part of the spreadsheet automatically update all related calculations throughout the document. VisiCalc transforms the Apple II from an expensive toy into an essential business tool. For the first time, business people can justify buying a personal computer because it can pay for itself by increasing productivity. Accountants, financial planners, and small business owners discover that VisiCalc can perform in minutes calculations that previously took hours or days. The Apple II becomes the first personal computer to achieve truly mass-market success. The success of the Apple II proves that there's enormous demand for personal computers, which doesn't go unnoticed by the computer industry giant IBM. For decades, IBM has dominated the mainframe and mini-computer markets, but they've largely ignored the emerging personal computer segment. The rapid growth of Apple and other personal computer companies finally gets their attention. In 1980, IBM makes a strategic decision that will reshape the entire computer industry. Instead of developing a personal computer using their traditional methods, which could take years, they decide to create a machine quickly using components purchased from other companies. They choose Intel's 8088 microprocessor for the brain, contract with Microsoft to provide the operating system, and use an open architecture that allows other companies to create compatible hardware and software. The IBM personal computer, introduced on August 12, 1981, is an immediate success. IBM's reputation for reliability and service gives businesses confidence to invest in personal computing. The PC's open architecture creates opportunities for thousands of other companies to develop software and peripherals, creating a vibrant ecosystem that drives rapid innovation and cost reduction. But IBM's decision to use standard components and an open architecture has an unintended consequence. Other companies can build compatible computers using the same components. Compaq Computer Corporation, founded by former Texas Instruments engineers, introduces the first IBM PC-compatible computer in 1982. Their machine runs the same software and uses the same peripherals as IBM's PC, but it's portable and offers better performance. The success of PC-compatibles creates a new industry structure. Instead of a few companies making complete computer systems, dozens of companies compete to provide processors, memory chips, disk drives, and software. This competition drives rapid improvements in performance while dramatically reducing costs. By the mid-1980s, powerful personal computers cost less than 10% of what equivalent systems cost just a decade earlier. The explosion in personal computer sales creates demand for new types of software. Word processing programs like WordStar and later WordPerfect replaced typewriters in offices around the world. Database programs like DBase allow small businesses to manage customer information and inventory. Games like Pac-Man and Flight Simulator turn computers into entertainment devices. But all of these programs share a common limitation. They're difficult to learn and use. Most software requires users to memorize complex commands and procedures. A typical word processing session involves typing cryptic commands like .pi to print a document or Ctrl-KD to delete text. Error messages are often incomprehensible, and getting help requires thick printed manuals. The solution to this usability problem is being developed at Xerox's Palo Alto Research Center, known as PARC. Xerox, the photocopy machine company, has invested heavily in computer research with the goal of creating the office of the future. Their researchers are working on technologies that will make computers as easy to use as copy machines. The breakthrough comes from recognizing that people navigate the physical world using visual cues and direct manipulation. You open a folder by reaching out and opening it, not by typing "open folder" into a keyboard. The Xerox researchers create a computer interface based on this principle, using pictures called icons to represent files, folders, and programs. Users interact with these objects using a pointing device called a mouse, invented earlier by Douglas Engelbart at Stanford Research Institute. The result is the Xerox Star Workstation, introduced in 1981. The Star's interface is revolutionary. Instead of typing commands, users point and click on icons. Files look like pieces of paper, folders look like manila folders, and trash cans look like waste baskets. To delete a file, you simply drag its icon to the trash can. To open a document, you double-click on its icon. The Star is incredibly advanced for its time, but it's also incredibly expensive, costing over $15,000. Most businesses can't justify such an expense for a single-user computer, so the Star fails commercially. But the ideas it demonstrates will soon transform the entire computer industry. Steve Jobs visits Xerox PARC in 1979 and immediately recognizes the potential of the graphical user interface. He convinces several Xerox researchers to join Apple, where they begin developing a consumer version of the Star's interface. The result is the Apple Lisa, introduced in 1983, which brings graphical computing to personal computers for the first time. The Lisa is more affordable than the Star, but still expensive at nearly $10,000. Like the Star, it fails to achieve commercial success. But Jobs and his team learned valuable lessons from the Lisa's reception. They realized that revolutionary interface improvements aren't enough if the computer remains too expensive for most users. Their next attempt is the Macintosh, introduced with a famous Super Bowl commercial in 1984. The Mac brings the graphical user interface to a computer that costs less than $2,500, making it accessible to small businesses and even some individuals. More importantly, the Mac is designed from the ground up to be easy to use. Its interface is consistent across all programs, and new users can become productive in hours rather than weeks. The Macintosh introduces interface concepts that will become standard throughout the computer industry. Windows that can be moved and resized, pull-down menus, scroll bars, and the desktop metaphor that treats the computer screen like the top of a desk covered with documents and folders. These innovations make computers accessible to people who have no interest in learning programming or technical details. But the Mac faces a significant challenge: software compatibility. The IBM PC and its compatibles now dominate the business market, and most software companies are reluctant to invest in developing Mac versions of their programs. Apple's insistence on controlling both hardware and software, while ensuring excellent integration, limits the Mac to a smaller market share. Meanwhile, Microsoft recognizes that graphical interfaces represent the future of computing. They begin developing their own graphical interface for IBM PC compatibles, which they call Windows. The first version, released in 1985, is crude compared to the Mac, but it runs on the installed base of millions of PC compatibles. The competition between different interface approaches drives rapid innovation throughout the 1980s. Computer screens become larger and more colorful. Mice become standard equipment. Hard disk drives replace floppy disks as the primary storage medium. Memory becomes cheaper, allowing programs to become more sophisticated and feature-rich. By the end of the 1980s, personal computers have evolved from hobbyist kits that require hours of assembly and programming into consumer appliances that ordinary people can use productively within minutes of unpacking them. Computers that once filled entire rooms now sit on desks in millions of homes and offices. Tasks that once required specialized training and expensive equipment, from word processing to financial analysis to graphic design, are now within reach of anyone willing to learn basic computer skills. By the end of the 1980s, personal computers have evolved from hobbyist kits that require hours of assembly and programming into consumer appliances that ordinary people can use productively within minutes of unpacking them. Computers that once filled entire rooms now sit on desks in millions of homes and offices. Tasks that once required specialized training and expensive equipment, from word processing to financial analysis to graphic design, are now within reach of anyone willing to learn basic computer skills. The personal computer revolution has fundamentally changed not just how people work, but how they think about information and communication. The computer is no longer a distant, intimidating machine operated by specialists in white lab coats. It has become a personal tool, as familiar and essential as the telephone or automobile, ready to amplify human intelligence and creativity in ways that its inventors could barely imagine. The graphical user interface has eliminated the barrier between human intuition and computer operation. Instead of memorizing cryptic commands and procedures, users can point, click, and drag their way through complex tasks using visual metaphors that mirror the physical world. This transformation has made computing accessible to millions of people who would never have considered using a computer in the command line era. The software revolution has been equally profound. Applications that once required teams of programmers working for months can now be developed by individuals using sophisticated development tools and programming languages. The economics of software development have shifted dramatically, enabling small companies and even individual developers to create programs that compete with products from major corporations. The competitive dynamics of the personal computer industry have driven unprecedented improvements in performance while simultaneously reducing costs. Moore's Law continues to deliver more powerful processors at lower prices, while competition among hardware manufacturers ensures that these improvements translate into better, more affordable computers for consumers. Most importantly, the personal computer has demonstrated that computing technology reaches its full potential only when it serves individual human needs and aspirations. The most successful applications aren't those that replace human capabilities, but those that enhance and amplify what people can accomplish. Word processors don't eliminate writing. They make it easier to revise, format, and share written work. Spreadsheets don't replace financial analysis. They make it possible to explore complex scenarios and perform sophisticated modeling. As the 1980s end, the personal computer industry is poised for even greater expansion. The foundation technologies are mature and reliable. Manufacturing costs continue to decline, while performance improves. Most importantly, a generation of users has grown up with personal computers, creating demand for even more sophisticated and capable systems. The next revolution is already beginning to take shape: the connection of personal computers to global networks that will transform isolated computing devices into windows into a worldwide web of information and communication. The personal computer revolution has put computational power into the hands of millions of individuals. The Internet revolution will connect those individuals to each other and to the collective knowledge of humanity itself. The year is 1989, and Tim Berners-Lee is frustrated. Working at CERN, the European Physics Laboratory in Switzerland, he's surrounded by brilliant scientists from around the world, each using different computer systems that can't easily share information. Physicists at CERN use VX computers, Unix workstations, Macintoshes, and IBM PCs. But getting a document from one system to another requires converting file formats, copying files to floppy disks, or printing and retyping text. There has to be a better way. Berners-Lee envisions a system where any computer anywhere in the world can access information stored on any other computer, regardless of what type of machine it is or what software it's running. He calls his idea the World Wide Web, and it will transform not just computing, but human civilization itself. The technical foundation for Berners-Lee's vision already exists in the form of the Internet, which has grown far beyond its origins as ARPANET. By the late 1980s, the Internet connects thousands of computers at universities, research institutions, and government agencies around the world. But using the Internet requires specialized knowledge and technical expertise. Most people access it through text-based programs with cryptic commands like Telnet and FTP. Berners-Lee's breakthrough insight is that the Internet needs a simple, universal way to link information together. He creates three key technologies that will make this possible: HTML, or Hypertext Markup Language, which defines how web pages are structured; HTTP, or Hypertext Transfer Protocol, which specifies how web pages are transmitted between computers; and URLs, or Universal Resource Locators, which provide unique addresses for every piece of information on the web. The concept of hypertext isn't new. It was proposed by Vannevar Bush in 1945 and developed by Ted Nelson in the 1960s. But Berners-Lee is the first to implement hypertext on a global scale. His system allows any document to contain links to any other document anywhere in the world. Click on a link in a document in Switzerland, and you might instantly access information stored on a computer in California. In December 1990, Berners-Lee creates the first web browser, which he calls World Wide Web, running on a NeXT computer. The browser displays formatted text and allows users to navigate between documents by clicking on highlighted links. On December 20th, 1990, he publishes the first website at the address http://info.ch/hypertext/www/theproject.html, explaining what the World Wide Web is and how to use it. Initially, the web grows slowly. It's used primarily by academics and researchers who already have Internet access. Creating web pages requires knowledge of HTML coding, and browsing requires specialized software that's difficult to install and use. But in 1993, everything changes with the release of a browser called Mosaic. Mosaic is created by a team of student programmers at the National Center for Supercomputing Applications at the University of Illinois, led by Mark Andreessen. Mosaic is the first web browser that's truly easy to use. It displays not just text and links, but also images embedded directly in web pages. More importantly, it runs on ordinary personal computers using Windows, not just expensive Unix workstations. The impact is immediate and dramatic. Within a year of Mosaic's release, web traffic increases by over 2,000%. Universities, companies, and even individuals begin creating websites. The web transforms from an academic curiosity into a global information system that anyone can use. Andreessen recognizes the commercial potential of web browsers and leaves the university to co-found Netscape Communications Corporation with Jim Clark, founder of Silicon Graphics. Their browser, Netscape Navigator, is released in December 1994 and quickly becomes the dominant way people access the web. Netscape goes public in August 1995 in one of the most spectacular initial public offerings in Wall Street history, with the stock price soaring from $28 to $75 on the first day of trading. The success of Netscape's IPO marks the beginning of the dot-com boom. Suddenly, investors realize that the Internet represents a massive commercial opportunity. Companies with little more than a website and a business plan attract millions of dollars in venture capital funding. Online bookstore Amazon is founded by Jeff Bezos in 1994. Auction site eBay, originally called AuctionWeb, launches in 1995. Yahoo begins as a directory of interesting websites created by Stanford graduate students Jerry Yang and David Filo. But the company that will ultimately dominate the web doesn't emerge from Silicon Valley venture capital. Instead, It starts as a research project by two Stanford PhD students, Larry Page and Sergey Brin. In 1996, they're working on a problem that's becoming increasingly urgent as the web grows. How do you find specific information among millions of web pages? Existing search engines like AltaVista and Excite try to index web pages by analyzing the words they contain, but this approach produces mixed results. A search for basketball might return pages about basketball equipment, basketball rules, basketball history, or pages that just happen to mention the word basketball in passing. Page and Brin realized that the key to better search results is understanding which pages are most authoritative and relevant. Their breakthrough insight comes from academia itself. In academic research, the importance of a paper is judged partly by how many other papers cite it. Page and Brin apply this principle to web pages, creating an algorithm they call PageRank. Their system judges the importance of a web page based on how many other pages link to it, with links from important pages counting more than links from obscure ones. The algorithm works remarkably well. Search results from their system, which they initially called Backrub and later renamed Google, are noticeably more relevant and useful than results from other search engines. In September 1998, they incorporate Google as a company, operating from a garage in Menlo Park, California, the same city where Hewlett-Packard was founded 60 years earlier. Google's clean, simple interface stands in stark contrast to other websites of the era, which are cluttered with advertising banners, blinking text, and multiple columns of links. The Google homepage contains nothing but a search box and two buttons, Google Search and I'm Feeling Lucky. This minimalist design reflects the founders' focus on providing the best possible search results rather than trying to keep users on their site as long as possible. As more people discover Google's superior search capabilities, web traffic grows exponentially. But search engines need a way to generate revenue, and the solution comes from an unexpected insight. Advertising that's relevant to what people are searching for is actually useful rather than intrusive. Someone searching for digital cameras probably wouldn't mind seeing advertisements for camera stores. Google introduces AdWords in 2000, allowing businesses to display small text advertisements alongside relevant search results. The AdWords system is revolutionary because it aligns the interests of Google, advertisers, and users. Advertisers only pay when someone actually clicks on their ad, so they're not wasting money on irrelevant impressions. Google makes money by facilitating successful connections between businesses and customers. Users see advertisements that are actually related to what they're looking for. This creates a virtuous cycle that generates enormous profits while improving the user experience. Meanwhile, the rapid growth of the internet is creating new challenges and opportunities. As more people get online, the demand for faster connections increases. The dial-up modems that most people use to connect to the internet are painfully slow by today's standards, transmitting data at just 56,000 bits per second. Downloading a single song takes 15 minutes. And downloading a movie is practically impossible. The solution comes from telephone companies and cable television providers who begin offering high-speed broadband connections. DSL, or digital subscriber line, technology allows existing phone lines to carry high-speed data while still supporting regular voice calls. Cable modems use the same coaxial cables that deliver television programming to provide internet access at speeds hundreds of times faster than dial-up modems. Broadband adoption accelerates throughout the 2000s, fundamentally changing how people use the internet. With high-speed connections, it becomes practical to share photos, stream music, and even watch videos online. This creates opportunities for entirely new types of websites and services. One of the most significant developments is the rise of social networking. The concept isn't entirely new. Bulletin board systems and online communities have existed since the early days of personal computing. But broadband internet makes it possible to create rich, interactive social experiences that weren't practical with slow dial-up connections. Friendster, launched in 2002, is one of the first social networking sites to gain significant popularity. Users create profiles with photos and personal information, then connect with friends and acquaintances. The site grows rapidly, but struggles with technical problems as millions of users overwhelm its servers. The real breakthrough comes with MySpace, Launched in 2003 by Tom Anderson and Chris DeWolf, MySpace allows users to customize their profiles with colors, music, and graphics, appealing particularly to teenagers and young adults. Musicians use MySpace to share their songs and connect with fans, creating a vibrant community around music discovery and sharing. But MySpace's dominance is short-lived. In February 2004, Mark Zuckerberg launches Facebook from his Harvard dorm room. Initially limited to college students, Facebook spreads rapidly across university campuses. Unlike MySpace's chaotic, customizable profiles, Facebook enforces a clean, consistent design that emphasizes real identity and genuine connections between people who actually know each other. Facebook's growth is unprecedented in the history of technology. The site reaches 1 million users by the end of 2004, 100 million by 2008, and 1 billion by 2012. As Facebook grows, it transforms from a simple social networking site into a platform that fundamentally changes how people communicate, share information, and understand the world around them. The success of social networking sites demonstrates the power of user-generated content. Instead of consuming information created by professional publishers, people are creating and sharing their own photos, videos, and thoughts. This trend accelerates with the launch of YouTube in February 2005 by 3 former PayPal employees, Chad Hurley, Steve Chen, and Jawed Karim. YouTube solves a technical problem that had limited video sharing, the incompatibility of different video formats, and the large file sizes of digital video. The site automatically converts uploaded videos into a standard format that can be played in any web browser, and it uses advanced compression techniques to make videos stream smoothly even over slower internet connections. The first YouTube video, titled Me at the Zoo, is uploaded by co-founder Jawed Karim on April 23, 2005. The 18-second clip shows Karim at the San Diego Zoo describing elephants. It's unremarkable content, but it demonstrates the site's potential. Anyone with a video camera and an internet connection can now broadcast to a global audience. YouTube grows explosively, reaching 2 billion hours of video watched monthly by 2007. The site becomes a platform for entertainment, education, news, and self-expression. Musicians use it to share their work without requiring a record label. Educators create instructional videos that reach millions of students. Ordinary people become celebrities by sharing their talents, opinions, or just their daily lives. The proliferation of user-generated content creates new challenges for traditional media companies. Newspapers, magazines, television networks, and radio stations that once controlled information distribution find themselves competing with millions of individual content creators. Some adapt by creating their own online presence, while others struggle to find sustainable business models in the new digital landscape. The transformation is accelerated by the rise of mobile computing. While personal computers made computing portable compared to mainframes, they still required users to sit at a desk. The next revolution makes computing truly mobile, allowing people to access information and communicate from anywhere. The foundation for mobile computing is laid in the 1980s with the development of cellular telephone networks. Early mobile phones are large, expensive devices used primarily for voice calls. But as cellular technology improves and costs decrease, phones become smaller and more capable. The first smartphones, like the Palm Trio and BlackBerry devices, add email and basic internet capabilities to mobile phones. These devices are popular with business users who need to stay connected while traveling, but they're expensive and complicated for ordinary consumers. Everything changes on January 9, 2007, when Steve Jobs introduces the iPhone at the Macworld Conference and Expo. The iPhone isn't just an improvement on existing smartphones, it's a completely different approach to mobile computing. Instead of a physical keyboard, it uses a large touchscreen that can display different interfaces for different applications. Instead of a stylus, it responds to finger touches with unprecedented accuracy and responsiveness. But the iPhone's most revolutionary feature isn't hardware, it's software. The phone runs a version of Mac OS X, giving it the power of a desktop computer in a device that fits in your pocket. More importantly, it includes a full web browser that can display regular websites, not just simplified mobile versions. For the first time, users can access the complete internet from anywhere they have cellular coverage. The iPhone's impact extends far beyond Apple. Google responds by developing Android, an open-source mobile operating system that phone manufacturers can use for free. Android phones from companies like Samsung, HTC, and Motorola provide alternatives to the iPhone while expanding the smartphone market to different price points and user preferences. The combination of smartphones and high-speed mobile internet creates entirely new categories of applications and services. Location-based services use GPS to provide directions, find nearby restaurants, or help people meet up with friends. Photo-sharing applications like Instagram, launched in 2010, allow people to instantly capture and share moments from their daily lives. Ride-sharing services like Uber and Lyft, introduced in the early 2010s, use smartphones to connect passengers with drivers, disrupting the traditional taxi industry. By the end of the 2010s, smartphones have become ubiquitous in developed countries and increasingly common in developing nations. These devices provide internet access to billions of people who never owned desktop computers, creating a truly global digital network that connects humanity in unprecedented ways. The transformation extends beyond individual devices to entire computing infrastructures. Traditional software companies sold programs that users installed on their own computers, but internet connectivity enables a new model: software as a service, where applications run on remote servers and users access them through web browsers. This shift, commonly called cloud computing, offers significant advantages for both users and software providers. Users don't need to install, maintain, or update software on their own devices. They can access their applications and data from any internet-connected device anywhere in the world. Software providers can update their applications continuously, fix bugs immediately, and scale their services to handle millions of users without requiring users to purchase and install new versions. Companies like Salesforce pioneer the software-as-a-service model for business applications, while Google introduces web-based versions of traditional Office software with Google Docs, Sheets, and Slides. These applications aren't as feature-rich as desktop alternatives like Microsoft Office, but they offer collaboration capabilities that desktop software can't match. Multiple people can edit the same document simultaneously, with changes appearing in real time for all collaborators. The success of cloud computing creates enormous opportunities for companies that provide the underlying infrastructure. Amazon, originally an online bookstore, becomes one of the world's largest technology companies by offering Amazon Web Services, which provides computing power, storage, and other services to businesses and developers. Microsoft transitions from a desktop software company to a cloud services provider with Azure. Google leverages its search infrastructure to offer Google Cloud Platform. As the 2010s draw to a close, computing has been completely transformed from its origins in room-filling mainframes operated by specialists in white lab coats. Powerful computers now fit in people's pockets and are connected to a global network that provides instant access to virtually all human knowledge. Software applications run on vast networks of servers located in data centers around the world. People collaborate on projects with colleagues on different continents as easily as if they were in the same room. By the end of the 2010s, computing has been completely transformed from its origins in room-filling mainframes operated by specialists in white lab coats. Powerful computers now fit in people's pockets and are connected to a global network that provides instant access to virtually all human knowledge. Software applications run on vast networks of servers located in data centers around the world. People collaborate on projects with colleagues on different continents as easily as if they were in the same room. The convergence of personal computing, the internet, mobile devices, and cloud services has created a new digital ecosystem that touches almost every aspect of modern life. People use computers to work, learn, shop, communicate, entertain themselves, and navigate the physical world. The boundary between digital and physical reality is increasingly blurred, setting the stage for even more transformative changes in the decades ahead. The internet has evolved from a simple network for sharing research data into the nervous system of modern civilization. Social media platforms connect billions of people in real-time conversations that span the globe. E-commerce has transformed retail, allowing consumers to purchase products from anywhere in the world with a few clicks. Online education has made high-quality instruction available to anyone with an internet connection, regardless of their geographic location or economic circumstances. Mobile computing has untethered people from their desks, making information and communication available anywhere cellular networks reach. Smartphones have become the primary computing device for billions of people, particularly in developing countries, where desktop computers were never widely adopted. These devices have created entirely new categories of applications and services, from ride-sharing to photo-sharing to location-based recommendations. Cloud computing has transformed software from products that users purchase and install into services that are delivered over the internet. This shift has enabled new forms of collaboration and data sharing while reducing the technical expertise required to use sophisticated applications. Small businesses now have access to enterprise-class software and computing infrastructure that would have been prohibitively expensive just a decade earlier. The combination of these technologies has created a global digital infrastructure that enables innovation at unprecedented scale and speed. New services and applications can reach millions of users within months of their creation. Ideas can spread instantly across continents, accelerating scientific research, cultural exchange, and economic development. Yet this transformation also raises important questions about privacy, security, and the distribution of economic benefits from technological progress. The concentration of digital services among a few large technology companies has created new forms of market power and influence over public discourse. The collection and analysis of personal data on a massive scale has enabled new forms of targeted advertising and personalization, but also raised concerns about surveillance and manipulation. As we look toward the future, the internet and mobile revolutions have established a foundation for even more profound changes. The next wave of innovation will likely center on artificial intelligence, quantum computing, and the integration of digital technology into every aspect of the physical world. The story of computing continues to evolve, driven by human curiosity, creativity, and the persistent belief that technology can be used to solve important problems and expand human potential. The year is 2010, and Geoffrey Hinton is about to resurrect a nearly forgotten field of computer science. Working at the University of Toronto, Hinton is experimenting with artificial neural networks, computer programs inspired by the structure of the human brain. Neural networks aren't new. They were first proposed in the 1940s and experienced periods of excitement in the 1960s and 80s. But each time, progress stalled when the networks failed to live up to their promise, leading many researchers to abandon the field as a dead end. Hinton refuses to give up. He believes that neural networks simply need more data and more computing power to reach their potential. In 2012, his team demonstrates that deep neural networks can dramatically outperform traditional computer vision techniques in recognizing objects in photographs. Their system, trained on millions of images, can identify cats, dogs, cars, and thousands of other objects with unprecedented accuracy. This breakthrough launches the modern artificial intelligence revolution. The key insight is that neural networks with many layers, called deep networks, can learn hierarchical patterns that mirror how the human brain processes information. Lower layers detect simple features like edges and corners, while higher layers combine these features to recognize complex objects like faces or automobiles. But training these deep networks requires enormous amounts of data and computational power that simply wasn't available in earlier decades. The timing is perfect. The internet has created vast databases of labeled information that neural networks can learn from. Smartphones and digital cameras have produced billions of photos, tagged by their owners. Social media platforms contain millions of text posts expressing human thoughts and opinions. All of this data becomes training material for artificial intelligence systems. Equally important is the availability of powerful computing hardware. While CPUs in personal computers have become faster, the most dramatic improvements have come in graphics processing units, or GPUs. Originally designed to render video games and movies, GPUs excel at the parallel mathematical operations required to train neural networks. Companies like NVIDIA, once focused primarily on gaming and entertainment, suddenly find themselves at the center of the AI revolution. The combination of deep learning techniques, massive datasets, and powerful GPU computing creates a virtuous cycle. Better AI systems generate more interest and investment, which funds research into even more advanced techniques. Tech companies begin hiring AI researchers by the hundreds, offering salaries that rival those of professional athletes. Universities struggle to retain faculty as students and professors alike are recruited by Google, Facebook, Apple, and other technology giants. Google demonstrates the potential of modern AI with spectacular public demonstrations. In 2016, their AlphaGo system defeats Lee Sedol, one of the world's strongest Go players, in a highly publicized match. Go, an ancient board game, has long been considered the holy grail of game-playing AI because of its enormous complexity. The number of possible board positions in Go exceeds the number of atoms in the observable universe, making it impossible to solve through brute force computation. AlphaGo succeeds by combining deep neural networks with advanced search techniques and reinforcement learning. The system learns by playing millions of games against itself, gradually discovering strategies that even human experts find surprising and innovative. Move 37 in the second game against Lee Sedol becomes famous in AI circles as a move so unusual that human commentators initially thought it was a mistake, only to realize later that it was brilliant. The victory sends shockwaves through the technology industry and beyond. If AI can master Go, what other human cognitive abilities might be within reach? The implications extend far beyond game playing to areas like medical diagnosis, financial analysis, scientific research, and creative endeavors that have long been considered uniquely human domains. Meanwhile, another AI breakthrough is quietly revolutionizing how people interact with computers. Voice recognition technology, which struggled for decades to understand natural speech, suddenly becomes remarkably accurate thanks to deep learning techniques. Apple introduces Siri in 2011, allowing iPhone users to ask questions and give commands using ordinary language. Amazon follows with Alexa in 2014, built into the Echo smart speaker that brings voice interaction into people's homes. These voice assistants represent a fundamental shift in human-computer interaction. For the first time since the development of graphical user interfaces in the 1980s, there's a genuinely new way for people to communicate with machines. Instead of clicking and typing, users can simply talk, making computing accessible to people who struggle with traditional interfaces, including young children and older adults. The success of voice assistants drives rapid improvements in natural language processing, the branch of AI that deals with understanding and generating human language. Google introduces the Transformer architecture in 2017, which becomes the foundation for increasingly sophisticated language models. These systems can translate between languages, summarize documents, answer questions, and even generate coherent text on almost any topic. The culmination of these advances comes with the introduction of ChatGPT by OpenAI in November 2022. Built on a massive transformer-based language model trained on text from across the internet, ChatGPT can engage in remarkably natural conversations about complex topics, write essays and stories, debug computer code, and explain scientific concepts. Within 2 months of its release, ChatGPT reaches 100 million users, making it the fastest-growing consumer application in history. The rapid adoption of ChatGPT sparks intense debate about the implications of artificial intelligence. Educators worry about students using AI to complete assignments. Writers and artists express concern about AI systems trained on their work without permission. Business leaders explore how AI might transform their industries, while workers worry about job displacement. But AI is just one of several revolutionary technologies emerging in the 21st century. Another breakthrough with profound implications is quantum computing, which harnesses the strange properties of quantum mechanics to perform certain calculations exponentially faster than conventional computers. Classical computers process information using bits that are either 0 or 1, like switches that are either off or on. Quantum computers use quantum bits, or qubits, which can exist in a superposition of both 0 and 1 simultaneously. This allows quantum computers to explore multiple solutions to a problem in parallel, potentially solving certain types of mathematical problems that would take classical computers thousands of years. The technical challenges of building quantum computers are enormous. Qubits are incredibly fragile and must be isolated from any environmental interference that might destroy their quantum properties. Most quantum computers operate at temperatures colder than outer space and require sophisticated error correction systems to maintain quantum coherence long enough to perform useful calculations. Despite these challenges, progress in quantum computing has accelerated dramatically in recent years. IBM, Google, and other technology companies have built increasingly powerful quantum computers, while startups like IonQ and Rigetti compete to develop practical quantum systems. In 2019, Google claims to achieve quantum supremacy by performing a specific calculation on their quantum computer that would be impractical on any classical computer. The potential applications of quantum computing are staggering. Quantum computers could break the cryptographic systems that secure internet communications, forcing the development of entirely new approaches to digital security. They might simulate molecular interactions with unprecedented accuracy, accelerating drug discovery and material science. They could optimize complex logistics problems, revolutionizing supply chain management and financial modeling. While quantum computers capture headlines, another transformation is quietly reshaping the computing landscape: the Internet of Things, or IoT. This refers to the connection of everyday objects to the Internet, embedding computing capabilities into devices that previously had no digital components. Smart thermostats learn household patterns and adjust temperature automatically. Fitness trackers monitor heart rate, steps, and sleep patterns. Connected cars provide navigation, entertainment, and diagnostic information. Industrial sensors monitor machinery and predict maintenance needs. Agricultural sensors track soil moisture and crop health. The number of connected devices is growing exponentially, with estimates suggesting there will be over 50 billion IoT devices by 2030. This proliferation of connected devices generates unprecedented amounts of data about how people live, work, and move through the world. Smart city initiatives use this data to optimize traffic flow, reduce energy consumption, and improve public services. Healthcare providers monitor patients remotely and detect health problems before they become serious. Retailers track customer behavior to personalize shopping experiences and manage inventory more efficiently. But the explosion of connected devices also creates new challenges. The massive amounts of data generated by IoT devices strain network infrastructure and data storage systems. Privacy concerns arise as more aspects of daily life become digitized and tracked. Security becomes increasingly complex as every connected device represents a potential entry point for cyberattacks. The solution to many of these challenges comes from edge computing, which processes data close to where it's generated rather than sending everything to centralized data centers. Instead of transmitting raw sensor data across the internet for processing in the cloud, edge computing devices perform initial analysis locally, reducing bandwidth requirements and improving response times. Edge computing represents a return to distributed computing architectures, but with modern AI and networking capabilities. Autonomous vehicles, for example, can't rely on cloud-based processing for split-second driving decisions due to network latency. They need powerful edge computing systems that can process sensor data and make decisions locally while still coordinating with other vehicles and infrastructure systems. The convergence of AI, quantum computing, IoT, and edge computing is creating new possibilities that seemed like science fiction just a decade ago. Autonomous vehicles are being tested on public roads, using AI to interpret sensor data and quantum-inspired algorithms to optimize routes. Smart cities coordinate traffic lights, public transportation, and energy systems in real time using massive IoT sensor networks and edge computing infrastructure. Healthcare is being transformed by AI systems that can diagnose diseases from medical images more accurately than human doctors. Quantum computers that might discover new drugs by simulating molecular interactions, and IoT devices that continuously monitor patient health. Education is evolving with AI tutors that adapt to individual learning styles, virtual reality systems that create immersive learning experiences, and IoT devices that track student engagement and comprehension. The workplace is changing as AI systems automate routine tasks, allowing humans to focus on creative and strategic work. Remote collaboration tools, accelerated by the COVID-19 pandemic, use AI to enhance video conferences, translate between languages in real time, and coordinate work across global teams. The traditional boundaries between physical and digital work environments are dissolving. But these advances also raise profound questions about the future of human society. As AI systems become more capable, what types of work will remain uniquely human? How will societies manage the economic disruption as entire industries are transformed by automation? What are the ethical implications of AI systems that can generate realistic fake images, videos, and text? How will privacy and individual autonomy be preserved in a world where every action generates digital traces? The answers to these questions will shape the next chapter of the computing revolution. Just as the personal computer, internet, and smartphone transformed society in ways their inventors couldn't fully anticipate, the current wave of AI, quantum computing, and ubiquitous connectivity will likely have consequences that extend far beyond their immediate technical capabilities. Looking ahead, several trends seem likely to define the future of computing. AI will become increasingly integrated into every aspect of digital life, from operating systems that anticipate user needs to applications that understand context and intent. Quantum computers will solve specific problems that are intractable for classical computers, particularly in optimization, simulation, and cryptography. The boundaries between physical and digital reality will continue to blur as augmented reality and virtual reality technologies mature. Brain-computer interfaces, still in early experimental stages, might eventually allow direct neural control of digital devices. Biotechnology and computing will converge as DNA storage systems archive massive amounts of data, and biological computers perform calculations using living cells. Yet for all the technical sophistication of modern computing, the fundamental drive remains the same as it was for Charles Babbage in the 1830s, augmenting human intelligence and capability. Whether it's a Victorian mechanical calculator eliminating errors in navigation tables, a 1970s personal computer empowering individual creativity, or a 21st century AI system accelerating scientific discovery, computers serve to amplify what humans can achieve. The story of computing is ultimately a story of human ingenuity and ambition. From Jacquard's programmable loom to quantum computers that harness the fundamental properties of reality itself, each breakthrough builds upon the insights and achievements of previous generations. The next chapters of the story are being written today in research laboratories, startup companies, and the imaginations of people who believe that the impossible can become inevitable. As we stand at the threshold of an era where artificial intelligence, quantum computing, and ubiquitous connectivity will reshape every aspect of human civilization, we're reminded that the most profound technological revolutions often begin with simple observations and bold questions. What seemed impossible yesterday becomes tomorrow's foundation for even greater achievements. The computing revolution that began with punched cards and mechanical calculators continues to accelerate, promising to transform human potential in ways we can barely imagine. The current wave of AI development represents both continuity and revolution. Like the personal computer revolution of the 1970s and 80s, AI is making powerful capabilities accessible to ordinary people and small organizations. Tools that once required teams of PhD researchers can now be accessed through simple web interfaces. At the same time, AI represents a qualitative leap forward, creating systems that can understand and generate human language, recognize patterns in complex data, and even exhibit forms of creativity. Quantum computing promises to solve problems that are fundamentally intractable for classical computers, potentially revolutionizing fields from drug discovery to financial modeling to cryptography. While practical quantum computers remain in their infancy, the rapid pace of development suggests that quantum advantages for specific applications may emerge within the next decade. The Internet of Things is creating a world where every device, vehicle, and appliance can communicate and coordinate with others, enabling new forms of efficiency and automation. Smart cities will optimize energy usage, traffic flow, and public services in real time. Manufacturing will become increasingly automated and responsive to changing demand. Healthcare will shift toward continuous monitoring and early intervention rather than reactive treatment. Edge computing is bringing artificial intelligence capabilities directly into cameras, sensors, and mobile devices, enabling real-time analysis of video, audio, and sensor data without requiring communication with distant servers. This will enable new applications in autonomous vehicles, augmented reality, and industrial automation that require split-second response times. The convergence of these technologies will likely produce innovations that we cannot yet imagine, just as the Internet enabled applications that were inconceivable when ARPANET was first developed. The key insight from the history of computing is that the most transformative applications often emerge from unexpected combinations of existing technologies, applied to problems their inventors never considered. Looking back over more than 2 centuries of computing history, from Jacquard's programmable looms to modern AI systems, several patterns emerge. Each major breakthrough initially seems impossible, then inevitable. Technologies that begin as expensive tools for specialists eventually become accessible to ordinary people. Applications that seem frivolous or impractical often prove to have profound implications for how humans work, learn, and communicate. Most importantly, computing technology reaches its full potential only when it serves human needs and amplifies human capabilities. The most successful innovations are those that make it easier for people to solve problems, express creativity, connect with others, and understand the world around them. The future of computing will likely follow this same pattern, with artificial intelligence, quantum computing, and ubiquitous connectivity serving as tools that enhance rather than replace human intelligence and creativity. The story of computing is far from over. If history is any guide, the next decades will bring innovations that seem as impossible today as smartphones seemed in 1970 or as the Internet seemed in 1950. The foundation has been laid by generations of inventors, engineers, and visionaries who believed that machines could augment human intelligence and expand the boundaries of human possibility. Their legacy continues in the work of today's researchers and entrepreneurs who are writing the next chapters in this ongoing story of human ingenuity and technological progress.